There is a topic in math called closure. A set is closed if you cannot escape from it. For example, the integers are closed over addition. Anytime we add two integers together, we get another integer. 2 plus 3 is 5. And the integers are also closed over subtraction and over multiplication. But the integers are not closed over division. 2 divided by 3 is 2/3. By dividing, we have escaped the integers because 2/3 is not an integer. But sometimes division doesn't escape. 18 over 6 is 3. 100 over 4 is 25. There are certain special cases where division gives us an integer. Now, we can take this idea of closure over integers and apply it to closure over polynomials. Just like the integers, polynomials are closed over addition. Any two polynomials added results in another polynomial. They're also closed over subtraction and multiplication. But polynomials are not closed over division. So here we divide one polynomial by another, and the result is no longer a polynomial. We've escaped the polynomials, since this has to be written using a fraction. But again, like the integers, sometimes division doesn't escape. Here we see an example of a polynomial division that results in a polynomial. So there are these special cases. And in this video, I'm going to give an overview of cyclotomic modifiers. This is a type of polynomial that I've found while studying cyclotomics, and these are closed over division. And they make a good topic for a video because they represent manipulations of sets of points on a circle. So we can visualize these sets of points. And let's start with a circle. And we're going to be using the unit circle, which means the center is 0. The point on the right is 1, and then the point on the left is -1. And multiplication we view as moving around the circle. So 1 times -1 takes us halfway around the circle, and then multiplying again by -1 takes us halfway around back to 1. -1 squared equals 1. Now let's add some more points. So if we go 1/10 of the way around the circle, we reach a point that we'll call z. And then another 1/10 gives us z squared, and then z cubed, z to the 4th. Z to the 5th is halfway around. It equals -1. And then we can continue adding these points until we arrive at z to the 10, which equals 1. So we have these 10 points, and these are called the 10th roots of unity. They're 10 evenly spaced points around the circle. And we created them by multiplying by z. But we didn't have to multiply by z. We could have instead multiplied by maybe z to the 7. So if we start with just 1 and multiply by z to the 7, and then again we get z to the 14 and then z to the 21, and we can continue doing this, and we see that it gives us all 10 points until we finally arrive at z to the 70, which equals 1. So z to the 7 gives us all 10 points. But this doesn't always work. Let's take, for example, z to the 4th. Multiplying again, we get z to the 8th, and then to the 12th, and then to the 16th. But then we arrive back at 1 with z to the 20. So we only got half of the points. All of the odd powers of z were missed. So z to the 4th doesn't behave very nicely, at least not in the way that we would like. So we're going to focus on these 4 points. These are the 4 that will generate all 10 points. And they are special. We call them the primitive 10th roots. They're primitive because they can get to any of the other ones. One thing that these numbers have in common is they have the same minimal polynomial. And this is phi, and this is a formula for phi. Phi has 2 properties. First is the 0 property. If we take z as an input, we get 0. Secondly, we have the division property. If there's some polynomial f that has z as a 0, then phi divides f. So phi is like the most fundamental polynomial with z as a 0. And we can also write this as saying that there exists some g such that phi times g is f. Now, I've written these two properties with z, but they also hold for z cubed, z to the 7, and z to the 9, because these numbers all act the same. So let's take a look at phi of z. When we write the formula on the right, we get these 5 terms, and we can plot them around the circle. And here I've put the positives in yellow and the negatives in red. Now, by the 0 property, this equals 0. And if you recall, 0 is at the center of the circle. And we can visually see that this equals 0. We'll put a vector pointing out for the positive and in for the negative. And then if we rearrange these so that the vectors are stacked together, we see that we arrive back at 0. So yes, the sum of these 5 points is 0. Now we've done this with phi of z, but we could also take phi of z to the 3rd. And that also has the 0 property. And let's look at this equation. This is phi of z to the 3rd, but we could instead view it as some function f that has z as an input. So these have the same output, we're just viewing the input differently. By the 0 property, this top line is 0, and since they have the same output, the bottom line is also 0. But by the division property, that means that phi of z divides f of z. So there's some g such that phi times g is f. And we can find g by dividing f by phi. So let's do that. We can write out f and phi, and then by calculating, we can find the resulting polynomial. This is what g equals. So we have the terms, but what is g telling us? What does this polynomial mean? Well, remember, phi times g equals f. But f was defined to be phi of x to the 3rd. And just to make things clearer, we'll show that the other two are taking x as an input. So phi of x times g of x is phi of x to the 3rd. On the left, we have the set of points from phi of z, and on the right, we have the set of points from phi of z to the 3rd. And g essentially moves us from the left to the right. Multiplying by g modifies the left set into the right set. So we'll call g a modifier, and we'll write it as m sub 3. 3 because we're going to z to the 3rd power. And the reason we write it this way is because this is not the only modifier. We could do the same process with z to the 7. So here on the right, we have the set of points created by phi of z to the 7. And again, we have a modifier, m sub 7. And this polynomial is a little bit larger. There are quite a few terms. And we can repeat this process also for z to the 9. There is an m sub 9, and here we see that polynomial. But this m sub 9 has a lot of terms. It's quite complicated, but it doesn't seem that it really needs to be. I mean, let's just look at these two shapes. They look very similar. They're just rotated versions of each other. So if we take the set on the left and rotate it around, we should get the set on the right. And what's the distance? It's z to the 6. So it seems like phi of x times x to the 6 should equal phi of x to the 9. That seems that it should be true. And so that leads us to wonder, is m sub 9 equal to x to the 6? M sub 9 has a lot of terms, so clearly these aren't exactly equal, but we want some way to think about them being the same. They act the same as modifiers. Well, the difference that we see, the set we get from m sub 9 has this middle point as z to the 18. But from z to the 6, we get z to the 8. Those points appear in the same spot, but they have a different power, 18 versus 8. So are those different points, or are they the same point? let's go back and recall that 1 equals z to the 10. When we multiplied by z 10 times, we got back to 1. If we start with z to the 8, that's equal to z to the 8 times 1. We can multiply by 1 without a problem. But by the equation above, we can substitute 1 for z to the 10, and then multiplying these together gets z to the 18. So yes, z to the 8 does equal z to the 18. So those two sets should be the same. And here's how we can think about that. We will subtract 1 from each side of this upper equation, and then we get 0 equals z to the 10 minus 1. So we want to work with polynomials treating z to the 10 minus 1 as 0. Okay, so we're saying that these two sets are equivalent. But if they're equivalent, we should be able to add 0 without a problem. Adding 0 doesn't change anything. And actually, we can add any polynomial h times 0, because the h will just get canceled out by 0. Now we substitute 0 for z to the 10 minus 1, and now we see those two sets are equivalent if they're separated by some multiple of z to the 10 minus 1. Now we can divide out phi of z. On the left, they just get canceled, but on the right, we get this term z to the 10 minus 1 over phi. And this term is called the reciprocal cyclotomic, and we write it using the Greek letter psi. Okay, so m sub 9 and z to the 6 are the same, they're just separated by some multiple of psi. And this equation here is true. We can calculate this and find a formula for h. So now we have kind of a special kind of equivalence. We'll write it out this way. Two modifiers, m and n, are equivalent if there is some polynomial h such that m equals n plus h times psi. In other words, modifiers are equivalent if they're only separated by a multiple of psi. So now if we return to our three polynomials, we can divide by psi and take the remainder, and we get these much nicer forms to deal with. And these polynomials are equivalent, at least as modifiers. Now, to get to these, we use the primitive 10th roots. So we'll change the notation a bit to add in that 10. And we're doing this because, yes, we use the primitive 10th roots, but we could do this for any number. For example, if we use the primitive 14th roots, we get these modifiers, and they do the same thing. So using the primitive 14th roots, we get this set of points for phi of z, and a different set of points for phi of z to the 5, and we have a modifier that can move from the left to the right. And more generally, with phi as the nth cyclotomic, and psi as the nth reciprocal, and z to the r as a primitive nth root, we will define the modifier of n on r as phi of x to the r over phi of x plus some multiple of psi. So this gives us a general form for that modifier. To look at a few specific cases, with r as 1, we always get 1 as a modifier, or something equivalent to 1. If we have a prime power, p to the k, the modifier also equals 1. And then m sub 2p, comma 2p minus 1 is x to the p plus 1. We saw an example before with m sub 10, comma 9 equals x to the 6. And we could continue looking at specific cases like this, but that could go on forever. And there's a more important question at hand. What about closure? I brought up this topic at the start of the video and haven't readdressed it. So let's go back to that. Returning to the 10th roots, we have this set of points from phi of z. And then we had these other three sets of points. And we found these modifiers that allow us to go from the middle to one of the other sets. But maybe a question is, can we go back? Are there some inverse polynomials, I for inverse, that will take us from a set back to phi of z? So as an example, maybe we'd want I sub 3 times phi of x to the third to equal phi of x. Now we could define I to be 1 over m, and then substituting we get this equation, and then multiplying out we get phi of x to the third equals m sub 3 times phi. And this is exactly how we defined m, so this is true, but the problem is this is a fraction. So we can define I to be a fraction, but perhaps it would be nicer if I wasn't, if I was just a normal polynomial. And it turns out we can find a representation of I that is just a polynomial. So let's take this equation. We can put in the explicit form of m, and then we claim that this equals I. So if we multiply the blue on both sides, and then expand that, we get this equation where we say that left side equals 1. Now this is clearly not true, but remember we can add some multiple of psi. So specifically we're going to add negative x to the 4 plus 1 times psi. And if we work this out, we see, yes, these two sides are equivalent. And that tells us that, yes, x to the 5th plus x squared minus x does act as I. This is an inverse. And so we can find inverses for 7 and 9 as well, which gives us a way to go back and forth. We can go from the inner set to one of the outer sets and back. And not only that, we can go between any two sets. So what if we want to go from phi of z to the 9 to phi of z to the 7? Well, we can first multiply by I sub 9 and then by m sub 7, and that will take us along that path. And so I sub 9 times m sub 7 gives us a direct path between those two sets. And we can find a similar path between any two sets. Now again, we've done this work with the 10th roots, but we can do this more generally. For any modifier m, there exists an inverse I such that m times I equals 1 plus a multiple of psi. And in order to prove this, we'll first remember that z to the r is a primitive root. What does it mean that it's a primitive root? If you recall from earlier, we start with 1 and then we multiply by a primitive root, and then at some point we get a point that's equivalent to z. So with z to the r, generally, if we multiply that enough times, say s times, we get z to the rs equals z. Although to make this truly equivalent, we might have to add some multiple of z to the n minus 1. So z to the rs is special. And going forward, we're going to look at the equation phi of x to the rs. But first, we'll take a little detour and just look at r. So there's some set of divisors of r, which we'll call d1, d2, all the way up to dA. And phi of x to the r can be written as the product of phi nd1 times phi nd2 multiplied all the way through phi nda. These terms are special because phi nd1 divides phi of x to the rs. And that's also true for phi nd2, phi nd3, all the way up through phi nda. And because all of those terms divide the blue term, that means that phi of x to the r also divides phi of x to the rs. In other words, there's some f such that f times phi of x to the r equals phi of x to the rs. And we will claim that that f is the I that we're looking for. That is the inverse. So let's bring this equation over, and we will recall from earlier, we said x to the rs equals x plus some multiple of x to the n minus 1. So we can substitute that in the right half of the equation. Okay, so the input on the right is x plus a multiple of x to the n minus 1, which means the output will be phi of x plus some multiple of x to the n minus 1. Now we'll multiply everything by m, and then we recall that m was defined so that m times phi of x is phi of x to the r. And this is the left side of the equation, so we can replace it with the right side of the equation. Now we will tidy things up a bit, and then we'll divide everything by phi of x to the r. Now on the left, that just cancels out and we get m times I. In the middle, that cancels out to 1. And on the right, we actually get some multiple of psi. Now the equation states that m times this supposed I does equal 1 plus a multiple of psi. So returning to our claim, for any m, there does in fact exist an I such that m times I is 1 plus a multiple of psi. And this means that if we treat psi as 0, then the set of polynomials generated by m and I is closed over division. If we want to divide by m, we can just multiply by I instead, and vice versa. And to state this in abstract algebra terms, this set forms a multiplicative group G sub n in the factor ring of integer polynomials over the ideal generated by psi sub n. For a prime power, this group has only one element, 1, so it's isomorphic to Z1. And for the interested viewer, I'll leave a question. What does G of 6 look like? And with that, thank you for watching. I hope you enjoyed this video. I have a few other videos on cyclotomic polynomials that I will leave a link to in the description. Now, one way we could define